So the previous two simple algorithms was for finite hypothesis class. Then what will happen for infinitely many hypotheses? So can we define a dimension of hypothesis classes with infinitely many hypotheses that characterize the best achievable mistake bound, like a VC dimension? So when we define peg learnability for hypothesis class with infinitely many different hypotheses, we use VC dimension. VC dimension, the definition of VC dimension is how many data points we can shatter. Okay, if our hypothesis class can make any different combinations of 0 or 1 for 4 different instances, then the VC dimension of this hypothesis class was 4. Okay, the VC dimension was for the complexity of hypothesis class that can discriminate data point or freely without any without any impossible combination for given instances. It's when we have 5 instances and the given hypothesis class can make any possible 0 or 1 combinations for these 5 data instances, then the VC dimension is n is 5. Okay, so from this shattering data point, we can define complexity of hypothesis class, and the complexity of this hypothesis class can define peg learnability. How many training instances do we need to make epsilon accuracy with probability 1 minus delta? So for the online learnability, very similar concept we can define as well, but with real different concept. No, exactly the same VC dimension is not fit for the online learnability, so we have to define something new, but quite similar. Okay, so here we want to define H shattered tree, a hypothesis class shattered tree. A shattered tree of depth D is a sequence of instances v1 to v to the d minus 1 in X input domain X, such that for all depths, we have the output of hypothesis v instance vit is equal to yt, where it is equal to 2 to the t minus 1 plus summation j1 to t minus 1 yj times 2 to the t minus 1 minus j. So okay, it is it's not easy to imagine the case shattered tree. So let's see this example. So this is tree with depth 3. So this is the first level, second level, third level. There is instance v1, instance v2, instance v3, instance v4, v5, v6, v7, and this branch, this h means for the first instance, hypothesis make prediction value 0. Okay, so the left hand side is making prediction 0. Right hand side is making prediction with value 1. Okay, so this is output 0, This is prediction 1. So all hypotheses among our hypothesis class making output prediction 0 will go to this direction. So there is some subset of hypotheses, and there are another subset of hypotheses. They are disjoint, but the union of these two hypothesis set will be the original hypothesis class. With the second instances, we will discriminate this branch. So we will discriminate this subset of hypothesis. Again, this branch means output prediction 0. This branch means output prediction equal to 1. Okay. This means 0. This means prediction 1. So again, there are subset of hypotheses. There are subset of hypotheses. There are subset of hypotheses. There are subset of hypotheses that make prediction 0, 0, 0, 1, 1, 0, 1, 1. Okay. For the V4, V5, V6, V7, we can make another cases. Make your prediction 0, 1, 0, 1, 0, 1, 0, 1. Okay. If all the rifts contain at least one hypothesis, then we can say that our hypothesis class can shatter this tree up to level 3. Okay. And the Ldim by Nick Littlestone. Ldim is the maximal integer t such that there exists a shattered tree of depth t. Okay, so in this case, Ldim of our hypothesis class is 3. Why shattered tree is useful to study infinitely many hypothesis class? Because we can say the mistake bound using the L dimension. No algorithm can have a mistake bound strictly smaller than L dimension. So we have this inequality. Why? So for instance, in this case, when we have L dimension 3, because every riff contains at least one hypothesis, here we can make the output yt so that the prediction and the output prediction doesn't match it. So for instance, if the P1 was equal to 0, then we can say the adversary can make y1 equal to 1 and then just consider this amount of hypothesis subset. And using V3 instances, if P2 is equal to 1, then we can go to here and make y2 equal to 0. Because there are still some possible hypotheses making y1 equal to 1 and y2 equal to 0 with instances v1 and v3. At the third level, again, we can make a y3 so that y3 does not equal to p3. So when our hypothesis class have shattered 3 to level 4, then we can make a mistake at least 4. If our hypothesis class can have shattered 3 up to level 2, then we can make a mistake at least 2. So the depth of shattered tree can tell us some lower bound of the mistake.